So I'm glad to announce the talk of Sasha Yom Din from Hebrew University on tempered representations.
Okay, thank you, Dima. Yes, okay, so we will want to talk about tempered representations. So let me first kind of recall what are they. So we will have some group, locally compact group. No, maybe second countable or something like this, and unimodular. And let me first recall Fourier theory. Maybe everyone knows, but this is my for G being abelian, in the case when G is abelian. So then you have the set of characters of G. The set of characters of G. Those are continuous homomorphisms. And then you have a Fourier transform if you have f function on G, and you generate a function on the set of characters by the following formula. You kind of average against f, use f to average the character. Okay, so yeah, so here of course, yeah, I fix some dg is a Haar measure on G, and you can summarize Fourier theory by saying that the L2 norm of f is equal to the L2 norm of its Fourier transform, which is the following thing. You take this, and so here you have the special feature that the set of characters is an abelian group itself again, and this is the Haar measure. Since it has some homogeneous structure, it's a group, you can take the Haar measure again. Of course, appropriately normalized. Okay, so this is Fourier theory, and then let us recall how to generalize this if G is not abelian. If G is not abelian, let us assume just for simplicity now that it is of type 1 for all the formulations to be nice. Then you have the notion of G irrep. So G representation, for us it will always be unitary in this talk. So you know it's a pair V pi where V is a Hilbert space and pi is a homomorphism from G to operators on V, some continuity property, and you have the notion of irreducible G representation. So V pi is a irrep if it has no invariant closed subspaces and it is not equal to 0. And then the replacement of the set of characters is, let us call it G hat, the set of isomorphism classes of the irreducible unitary representations. Yes, of course, there is always an embedding. I denote it like this: a character gives rise to one-dimensional representation on which G acts by this character, but this is not surjective unless G is abelian. And now, so how to phrase the generalization of Fourier theory? So again, if you have f a function, scalar valued function on G, you produce f hat. It is a function in quotation marks on G hat. So namely f hat of irreducible representation is an operator on V. And it is defined basically by the same formula. It is an integration against f of the operators that the representation provides. And then, yes, so basically, and then you want to say, you have the same formula. You would like to say that the L2 norm is equal. Yes, so this is the basic theorem. Then here you had the theorem. And here, so again you integrate f hat. Yeah, so here let me abbreviate always. Instead of v pi, I will always write v, and instead of pi of G applied to V, I will always write GV. So here, okay, so here this is the formula, but so here first, instead of absolute value, this is an operator. So you take Hilbert-Schmidt norm, and so here you also need some measure. In the abelian case, you had the Haar measure because the characters was a group, but in this case, this is kind of not very homogeneous in general. So there is some measure. So the claim, the theorem recasts into that there exists a unique measure dv on G hat such that you have such a thing. And this is called the Plancherel measure. Okay, do you have questions? So now in principle, so this is a good question, I guess, to find the Plancherel measure.
So the measure depends also on what what specific Hilbert structure you choose on each representation. Yes.
Well, I don't know what you mean by specific. Multiplying by a scalar or
yes,
something more serious?
No, just scalar, but each representation different.
I think it cancels. It doesn't depend, no.
If you
I think you only can define the class of measure, right?
Well, the measure depends on the Haar measure on G, but I think Rami asked something different. If
not Haar measure on G. Just if you take half of the big chunk of representations, irreducible representation, and fix a different scalar product on them, say multiplying it by 2. So you have to divide the measure by 2 to get the same formula to hold.
I think the Hilbert-Schmidt norm will not change. It's like scalar matrix commutes with all matters. I think you will not have it.
We say that when you change the scalar product on V, the Hilbert-Schmidt norm on end V does not change?
Well, yes, because
if V is one-dimensional.
So it's like
you're right.
Trace.
Yes, you're probably right.
F squared.
I see.
Anyway, yeah, I think I'm right, but let's not take. Maybe you can figure out meanwhile.
So it's actual measure on the set of irreducible representation, just well-defined measure, yes?
Yes, up to that it depends proportionally on the Haar measure on G.
Yeah, we okay.
Yes. Yes, so it's a well-defined measure. Again, I said our group is of type 1, that one can ask about describing. But okay, the question we want kind of is much cruder. You can ask about the support of this measure, support of the Blancherel measure, because G hat has natural topology, the Feld topology, and you can define the support as biggest closed subset whose complement has measure 0. And so you have the question of support, and irreps in the support are called tempered, yes. So our basic question is to, well, not question, but our basic object, we want to talk about tempered irreducible representations. Well, you can define tempered also if the group is not of type 1. It's in the closure of the regular representation, but let me now we just motivated why it's a basic object, because so in other words, tempered irreducible representations are those which contribute to the spectral decomposition of functions on the group itself. Well, and now I want to recall basic definition properties of the basic class of tempered representations, which are the square integrable representations. Irreducible representations. And so G irrep V is a square integrable if you can formulate several equivalent conditions. So first is that the Blancherel measure of the singleton consisting of V is positive, is not 0. So in other words, it contributes, how you say, discretely or atomically, I don't know, to the Blancherel measure. And a second more structural condition is that V is isomorphic to direct summand in the regular representation. Well, yes, G is unimodular, so you can consider it left regular or right regular, doesn't matter. And third condition is that all matrix coefficients, which I will now recall definition, all matrix coefficients of V are square integrable, so they lie in L2 of G. Yes, matrix coefficient, let me remind, is a function on G of the form G maps to inner product like this. You fix two vectors, so you have a lot of matrix coefficients associated to every given representation. And let me now recall kind of a basic property of square integrable representations, which is kind of a sure orthogonality properties. So if V is square integrable, there exists a positive scalar. It's called the formal dimension of V, such that for all pairs of matrix coefficients, you will have the following formula. So you ask about the inner product of two matrix coefficients, which makes sense because the matrix coefficients of a square integrable representation are square integrable, and this will be equal, kind of by Schur's lemma, basically to the inner products of the vectors you started with. but with some scalar of proportionality, and this is the reciprocal of the formal dimension. And yeah, so the motivation is, I guess, from the case if G is compact, then all irreps are both square integrable and finite dimensional. And in this case, the formal dimension is simply equal to the dimension. And also you have the following property that the Plancherel measure of the singleton we talked about, which is positive, like we said, for square integrable representation, is actually equal to the formal dimension. So this is the basic properties of square integrable representations. So yeah, so in some sense, I guess from Bernstein, I learned this kind of, I don't know how to say, phrase or something. So in some sense, analytically, they are completely understood once you have a square integrable representation, but it is not clear how to construct such representations. You can say in some sense you have the opposite for you know, like parabolically induced representation. You have a clear procedure how to construct them, but they are more difficult analytically. So there is a.
We completely understood analytically.
Well, I mean, more or less this kind of all what we said. They are just discretely embedded and
the square integrable representations. Yes.
Yeah. Yes. Yes, but this doesn't mean that they are understood in the sense of which ones you have for a given group. So it's opposite kind of in some sense sometimes for some classes of groups. Those are which are easiest once you have them, are hardest to. Yes. Anyway, so what is our goal in this talk is is to try to precise this vague idea that vaguely the tempered representations are those which are so let me say like this, on the verge of being square integrable. And so there are various classical ways for specific groups to precise this idea. So in some sense, we want to try to give another formalization of this idea. That we had this nice class of square integrable representations, and in some sense, the tempered ones are those which are almost square integrable in some sense, in some kind of asymptotic sense of as you grow on the group or something like this. And okay, so to motivate this, I will first recall some special case of amenable groups. And there we will see some properties which we would like in some sense to generalize. So let me recall. So G is called amenable. Amenable if all G irreps are tempered. Yes, the support of the Plancherel measure is the whole G hat, and it can be shown that there is one kind of the worst, that if that it is enough to check on it, and this is the trivial representation. If the trivial representation is tempered, then it turns out that already all others are. Okay, and now I want to recall this so-called Faulner condition.
Is for you a definition of a minimal, or it's just?
Yes, for me it's definition. Of course, you're right. There are several dozens of other definitions equivalent.
But the if is if and only if. Yes, this is basically my question.
This one?
No, the first one before.
This one?
If yes. If
yes. In a definition, I don't like to write if and only for some reason. Yeah, I understood you. Okay, you're correct. Better to write like this. And okay, now let me recall Faulner's condition, which is another thing which is equivalent to this thing. So this condition is about the existence of some sequence of subsets. Okay, measurable, let's say, of finite volume, subsets of G, of finite non-zero, let's say, volume subsets of G, with the following property, that given any compact, for every compact K in G, you have the following property, which we will try to interpret. So you take the volume of Fn, and then you take the volume of Fn, so symmetric difference with its shift. And you want it to go to 0. So intuitive. So what does it mean? If we have Fn and we shift it a bit, and we want to see that the shift is almost the same as this Fn, meaning that the symmetric difference has small volume compared to Fn. Volume is with respect to the Haar measure, of course, and so in such a symptotic sense. And I want to interpret this kind of just non-formally, just in the mind, as kind of a formalization of this idea. So in which sense? So we can think as follows naively: if we have F in G, which is a G invariant of a finite non-zero volume. Of course, if G is not compact, there are no such Fs, but if we
G invariant meaning the entire G, no?
For the entire G. Just kind of, for intuition, of course, there is no such F.
But even if G is compact, then it's just the entire G, yes?
If G is compact, there is such F, yes.
But then it's the entire G, yes?
Yes. And then we can interpret such an F. We can have an embedding of into the regular representation of the trivial representation just by this characteristic function of this F. And like we said, this is one of the characterizations that the trivial representation would be square integrable. So in some sense here, the sequence of Fn's is a sequence which kind of is almost G invariant. It becomes more and more kind of, so to speak, in this precise sense. So in this sense, you can think that you have you almost have embedding of the trivial representation into the regular representation. So kind of the trivial, yes, you can think you have maybe such maps, but they are not G-morphic. but they almost become a geomorphic as you go, as you increase tensor. So you almost have an embedding. So the trivial representation is almost square integrable. So in this sense, I want to interpret that this condition gives some, maybe you can say geometric, because you deal with subsets of G. So in some geometric formal interpretation of this slogan. This is interpretation. What would it mean for the trivial representation to almost embed geomorphically into the regular representation?
Mm-hmm. So I have a question. So in order everything to work, in order to have this notion of tempered representation with this definition, you want everything to be of type 1, yes?
And no, so maybe it's confusing. I confused. Type 1 was just in order to have the Plancherel measure. Otherwise, you still have the notion of tempered representations and this amenability. Nothing changes. It was just for motivation.
So amenable are not necessarily of type 1?
No. Type 1, yes, maybe it's a bit confusing. It was just for in order to recall the nice decomposition. If you're not type 1, you still have the compositions, but more than one. And it's kind of
so how you define? How
you can have the regular representation being a direct integral of several different families.
Okay, and who is tempered now?
So they all will be tempered, kind of. Everyone which can appear in some decomposition.
Okay.
Okay, yes, so it's more kind of exotic, let's speak in quotation marks, when it's not type 1, so maybe.
But in general, it's not true that amenable are type 1, or is it? I don't know.
No, I don't think it's true. I don't see why. Yeah, type 1 was just, for a moment, to recall here this Plancherel formula.
No, but you use Plancherel formula in order to define the Plancherel measure, and then
you're right in the lecture, but
okay.
You don't need to. So I have a small mistake in my deduct. Yes, yes. In general, you still have the Fell topology, and you can still say that tempered irreps are just in the closure of the regular one. There is no difference.
What is regular?
The regular representation.
The
L2 of G.
What do you mean the closure? Just the closure of this one point with respect to the Fell topology, yes?
Yeah, so in general, you can have Fell topology not only on irreps, but all reps. And you have this one, and you can take the closure. And
it's a very short definition.
Yes, so there is no problem. You're right, I was a bit not clear at that point. Yes. Okay, so now we want to give kind of the basic, maybe semi-speculative, but basic definition that you can think from some direction as generalizing this Faulner condition. Maybe it has motivations from other directions. But so now we forget about amenable groups, just again for our general group G.
Sasha, I didn't understand. The Faulner condition, it kind of implies that that almost implies that there is trivial representation in L2. But then what about so this means that the trivial is square integrable. That the trivial is almost square integrable.
Yeah, I want to interpret this like this.
I see.
That it asymptotically becomes kind of square integrable.
I see. Thank you.
This is just my kind of point of stress, how to say, I want somehow try interpret this condition, and I say I want to interpret Faulner condition as a formal interpretation of this idea in this particular context. And now I want to generalize this. So to try to give a definition, if V is an irreducible representation of, again, now not amenable, just some group like we had G. So I want to give some definition of when V is kind of satisfies Faulner condition in some sense. So we call it, let's say, C-tempered. So we say that it is cis-tempered again if there exists a sequence, or maybe it's part of the definition. You know, I don't now care too much. So Fn are again of finite volume, finite non-zero volume, and okay, and the unit vector which will turn out to be not really an important choice, but it's convenient for now in the definition to have it. So V is cis-tempered if there exists a sequence like this and the unit vector such that the following two conditions that I will write are satisfied. So let me maybe start with the second condition because it is the direct analog kind of Faulner's condition. So for every two vectors in V and compact K, we have, so I write more or less a similar thing to what we had before. But now the replacement is that I need somehow, instead of volume, take something that somehow uses the representation that we have. So we take the integral instead of the function 1, which would give the volume. We take the integral of this square matrix coefficient of this kind of a pivot vector V0, which we fixed. And upstairs, we again take the symmetric difference and take this modified measure kind of it. But we take it for any kind of two vectors which we had. And the first condition is
so presumably G1, G2 are in K, right?
Yes, thank you. Okay. And upstairs I also wrote okay. And the first condition is oh yeah, what happened to this screen? Something moved. Yes.
So you take the matrix coefficient, and then you move it with you restrict it only to F, and
you kind of can think maybe it's the volume of Fn, but with respect to this new measure.
Matrix coefficient. I see.
Density, the new density. You have a density which is square matrix coefficient.
So if it is square integrable, then I can just take basically any Fn that I want, and it will work. Or
yes. If square integrable, then basically you can take some ascending sequence which exhausts the group or something like this. Yes. So let me just write the first condition. It's kind of a helper condition because in our context now we have a lot of vectors, not like in the trivial representation. So somehow I want to demand that the things for them are bounded in terms of things for our V0. Without taking even symmetric difference, just on Fn itself, I want the situation for any two vectors to be bounded by that of V0. So this is a kind of. Yeah.
What happens here in the square integrable case? Then just the numerator and the denominator are both bounded?
Yeah, bounded from away from 0 and infinity. So it's So it's kind of trivial for square integrable. Everything here is trivial. And and then of course, okay, and then we show you can consider it as an easy thing. Let's say that C-tempered irreps are tempered. But then the non-easy thing, so let me formulate as question. I think Kazhdan didn't want to formulate it as conjecture. So question is when or what, you know, what tempered irreps are C-tempered.
So another question. So I understand why I can think of two as some kind of almost square integrable, but one looks something different.
So one somehow, yeah, it somehow floated up when you want somehow to control the situation for the Hilbert space using, you know, something like Banach.
One and two are not equivalent. You ask both things, yes?
Well, speculatively, you can ask, maybe I just need one vector V0, and here everywhere I just need to know for this V0, I don't know the answer. Maybe it's enough just to know for some V0. I didn't.
Just a moment. In two, you do on the numerator V1 and V2, and the denominator you do V0, V0?
Yes, and in V1 also, in one also.
Yeah, in one I understand, but in two, why you do it in two somehow?
Well, this is the thing I know to work with nicely. Again, you can ask, maybe it's always happens so that if you just demand for some V0 like this, then everything else.
Or maybe for V1 and V2, but then to put it both in the numerator and the denominator. And it's okay because of one, yes. Because of
Yes.
one, put V1 and V2 both. You can change two.
Well, once you want to modify, you can ask also to modify ones, and I don't know. You can ask a lot of modifications. So I'm not sure. Maybe
but just one is not talking. So it might be that the function is very much not, the matrix coefficient is very much not square integrable, but they are all equally bad. Yes, when you
yeah, exactly. So we will now formulate. They grow in the same way. Yeah. So we will now formulate what you say. I think, if I understood you. So you have namely you want a proposition which is the analog of that one for square integrable representation of sure orthogonality.
Okay, never mind.
So this is as follows. V is a C-tempered.
Please mute yourself because you are not speaking.
A lot of
Dima, it is Arya. Can you put Arya on mute?
So if you have a C-tempered G-rep with Faulner, yeah, with the data we said, Fn and unit vector V0, then you have for all V1, again, two matrix coefficients. So again, you again want to take the inner product of two matrix coefficients, but of course this time they are not square integrable, so the product doesn't converge, the inner product doesn't converge, but you can take it relatively naturally once you have the setup on Fn, and you can normalize it by this basic kind of measure we already encountered. And then the claim is that if you, after this normalization, this I think what Rami was saying, you recover such a sure orthogonality relation, yes, a formal dimension relation. Well, you don't have here formal dimension because it's kind of swallowed in this term. In particular, if you think from this, just a small side observation, if you now would take a different unit vector and you plug in instead of this V's, you will obtain that there is the same growth for all unit vectors, something like this. And this means that the choice of unit vector was in fact immaterial, yes? In the definition, you don't really, it's convenient at first to use it, but in fact, they all are suitable. Okay, so this idea that after, so you kind of have almost inner product after this renormalization, you again have formulas which you would expect from sure orthogonality or inner products and so on. G-invariant inner products. And indeed, kind of the proof is using not sophisticated too much, using Banach-Alaoglu. You kind of find a weak limit, and so that, so to speak, such a renormalized inner product actually becomes an inner product. Yes, some vaguely speaking, this is the idea. Okay, so so maybe I try to say a brief remark, a vague remark. You can ask, if you know, of course, there are various classical formulations of water-tempered irreps, that the matrix coefficients are almost L2, or it's bounded by Harish-Chandra's psi functions. There are various classical formulations, but for some groups, not all groups, say reductive groups. And you can ask how it relates. So I think if I want to say vaguely how it relates, how I see the main difference, then it is the following: that classically you have the following ingredients. You fix a group, and you have your tempered irreps, and then kind of typically, let's say for a reductive group, you have the worst one with the slowest decay of matrix coefficients, and kind of a criterion of being tempered is a criterion of being dominated by, say, the worst matrix coefficient of this one, typically Harish-Chandra's psi function. Yes. So the condition is uniform, whatever tempered irrep you take, or whatever irrep you take, you want to ask, is it tempered? The condition is the same. It should be bounded by this, say, psi function, or this is the spirit. And somehow in our definition, if you take a tempered irrep which lies kind of below, has actually nicer decays than the worst one, to check that it's C-tempered will be much more difficult, because somehow the definition is adjusted, the growth is adjusted to the representation itself, and not the worst one among the representations of G. It is kind of self-checking, not with relation to other beings. So self-observing. So analytically, typically, what we will see now for SL2R, how it manifests typically analytically, is that you have a simple kind of estimate that the absolute value of the integral is smaller or equal integral of absolute value. Well, here the integral.
Can you repeat the previous remark? I think I didn't understand it.
So we will see it more precisely now for SL2R. Maybe I do again wrong didactically. I do it the opposite order. I first say the remark and then. But I wanted to say kind of that this definition, it's much harder to check for. We will see now for representations which are not of the worst behavior, because somehow it checks how the representation relates to itself and not to the worst possible behavior. But we will see now more quite, I think, clearly on SL2R.
You mean tempered representations which are not the worst among all tempered, or non-tempered?
Yeah, let's say tempered which are not. Yeah, and you want to show they are C-tempered, and you will have difficulty. So basically the idea is that to check that you are tempered by the criterions that you are bounded by the psi function, say, it will be enough to have a crude estimate of the form that absolute value of integral is smaller than integral of absolute value, where the integral here is the expression for the inner product you need to check, the matrix coefficient. But the matrix coefficient, you have the integral which expresses matrix coefficient for these representations I mentioned, which are not the worst. They kind of have a oscillatory behavior. and this estimate will be enough to check that they are not worse than the Xi function, but will not be enough to check our condition. So in order to check our condition, you will have to account for the cancellations kind of, so it's something more intricate. So yes, so maybe I say ahead of time what we will exactly see for SL2R. But this I just wanted maybe to remark how it relates to other criterions of being of being tempered. So each representation is by itself and not just something for the whole group. Yes, so also we have a constraint of time. So I wanted next just to say briefly, so we don't, most of the questions you can ask naturally we don't know, but we checked for SL2R that indeed all tempered irreps are C-tempered, and also for over p-adic field, PGL say. So for them we checked, and I wanted to briefly say how it looks like for SL2R. Plus we have a time constraint. So for SL2R we have some square integrable representations which from this perspective are not interesting, and we have some tempered irreps. So two family unramified principal series and ramified principal series. So just it's similar. So let me just consider the unramified principal series. I will call them VS. So VS are some tempered G irreps where S is a parameter in R. And so here V0 is the worst one, like I said, and VS for S not equal 0 are better than V0. So somehow in the apex you have one which is worse than the others. So yes, I wanted here to recall again, what is VS. So very briefly, it consists of functions on the punctured plane, which have some homogeneity, and what was the homogeneity minus, or I forgot, plus, and you consider the inner product, which is an integral over the circle embedded in the plane in the usual way, and you use kind of the uniform standard measure on the circle you would take, and you have this tempered principal series irrep. And then the claim is that each such VS is C-tempered.
So
with
this is unramified, yes?
Yes, ramified you will have the same. I just don't want.
Ramified you also need the sign of T, yes?
Yes. Yeah, the formula will be different. You will have a sign. The theorem will be the same. So each one is C-tempered with Faulner sequence. We take a natural sequence which you have for a reductive group. So here I index it by real numbers, but it doesn't matter. It's in the sense that you take any sequence of R which converges to infinity, it will serve as a Faulner sequence. So here FR is consists of matrices of operator norm smaller than e to the R.
And larger than e to the minus R?
No, because I think we're in SL2, so
SL2, sorry.
There is some bound.
Sorry.
Yes, so basically this, but we can be more precise. For example, we would like to say what is the growth if you take a unit vector in VS. You would like to ask what is the growth?
So the exponential here make any difference?
Well, here not. But now when I write the growth, it makes the obvious reparameterization difference. You can, it's just more natural to formulate like this. But, Yes. So here you can compute the growth you have. So here this means that the quotient tends to some positive number, not necessarily 1. And then what you can do, you can write the sure orthogonality relation, but using you can try replacing. If you replace this factor which we had by this factor, so maybe let me say ds is equal to 3 or 1 if s is 0. So you can try to replace by this polynomial factor. Well, then you will have the same formula, but there will be some normalization factor here because this means that the quotient tends to some positive number. And again, you can call it maybe something like formal dimension at the point S. And then you can call, for example, for SL2, you can calculate by hands that if you take this this measure, this is the Plancherel measure. Well, of course, restricted to the relevant subset on which we describe. So in some sense, it's again you have something analog to the thing you had for square integral representations, that this normalization factor describes the Plancherel measure. Here I should note there is some work of Ankabut, which I think it does such a thing more generally, but I didn't check precisely. I just mentioned because I saw it talks about something like this, so I mentioned there is some work about this. Yes, so sorry, I now spoke a bit faster because I was afraid about the time. So again, we have here the pictures that indeed the representations are C-tempered, and we have it's easy to calculate the precise growth, and you have such again, you can interpret the sure orthogonality, you can extract some kind of, so to speak, formula for the Plancherel measure from it, and here I wanted to comment about the proof, and also of course you can say so you can try to formulate something similar for general reductive groups, but this we don't know how to prove.
So where do you see the problem with oscillations that you?
Yes, so the problem with oscillations is when I try to explain how we prove for SL2R. So in the explanation, you use a Hilbert basis of VS, which is just the monomials, the trigonometric monomials on the circle. It is this formula on the circle, and since F is homogeneous, it extends uniquely. You have this standard K-finite basis, yes, and then I will not explain now because we don't have time, but you can reformulate using Fourier decomposition with respect to this basis. You can reformulate that our claim will follow if we can show that the following behavior of matrix coefficients of these basis elements. So here you take, on the torus as usual, and you want it to be less equal. Again, some here this depending on S equals 0 or not 0, such a thing. So here let me comment two things. So one thing to appreciate, kind of, one thing is that if C is allowed to depend on N and M, this is kind of, I don't know how to say, classical, let's say, yes. Then this is just because every matrix coefficient by itself, it's very classical theory of the asymptotic expansion and how it behaves and so on. So of course, you know such a thing. But the point here is simply that you want C to be uniform in all N and M. And also another remark, again, we don't have time, that if S is 0, this is easy, just like I said, it's absolute value of integral is smaller or equals an integral of absolute value, and you get this. And the problem is how to see this for S not 0, is that you have such a uniform bound of matrix coefficients. And we did it quite a long time effort with Pavel Ettinghoff. But then after we did it, I found that some people did it. I write their names by a bit different method. So they used the van der Korput lemma, and we used Pavel taught me WKB method. And I have here a picture. So I will have 3 minutes and I finish. So basically, here it's a picture of the matrix coefficients as a function of R, but slightly different normalization in the graph. And if you go from red to green to blue, it's like you can think we make our N and M bigger. We have parameters N and M. And we want to show that the functions are uniformly bounded by the same number, which does not depend on N and M. So basically the red, green, and blue are bounded by the same bound.
Who are N and M?
What?
Who are N and M?
N and M, we have here matrix coefficients of 2 basis elements. You want to show that you have a bound which doesn't depend on the basis elements. And you see, so I think here, I'm not a great analyst, not great anything, but definitely not great analyst. But I think if I understood the intuition is as follows, that as you make N and M bigger, kind of the energy of your solution becomes bigger and bigger. And then if I understand the intuition, a big energy can go on making your solution very big, to have very big values, but it also can go into making it oscillate fast without increasing its values indefinitely. And we kind of need to see that the latter is what happens, that they're bounded, but they become more and more violent kind of in their bounded realm. So you need to see it somehow. And there are techniques in analysis of solutions of second order differential equations for analyzing this and so on. But again, there are also other methods like these authors that I said to see this claim. Anyway, for p-adic group, you also have some similar claim, and there are a lot of questions which we don't know. And, thank you.
Very much. Questions, please.
So let me ask you, so first, just curious, I mean, it's very nice. If you did this analysis on the K type, but what kind of analysis if you work with the model of functions on the line instead of function on the circle? Does it, I mean, is it more or less equivalent problem, or does it?
Yeah, I think more or less this is maybe what these authors, they computed the inner product using the model on the line, and somehow their van der Korput lemma helped them. And yes, maybe if I understand correctly, this is the answer to your question, that it's also possible.
And harking back to something that you said before,
yes.
So for amenable group, the trivial representation is kind of the most, the extreme point in the tempered, so the most non-tempered, but of course still tempered. And for the reductive groups, we know that we have this Harishchandra Xi function, which comes from this most non-temporal. So is it something, if you try to analyze in general kind of the maximal objects in some sense?
Yeah, I don't really know, but we looked, for example, tried to see some literature for free groups or hyperbolic groups, and it seems there you also have such things, that you have this maximal, there is name for it in ergodic theory, I forgot, just the representation on the L2 of the boundary. Basically, it is the maximal one.
I see. So,
but I don't know the precise picture, but I guess usually all other are strictly maybe worse than it, strictly better. And Koopman, I think it's called Koopman maybe representation, something like this. For some classes, yeah, hyperbolic groups, which they like, you have this boundary and then you have L2 of the boundary, and it is the worst one, I think.
Sasha, I have two questions. First, yes. I somehow missed what is the state of the art? Is the question known for SL2?
SL2 are PGL, yeah. Yes, so basically, yes, for SL2 we calculated.
So tempered and C-tempered is the same?
Yes.
And in general, do you expect them to be the same?
Sorry, SL2, but SL2C we didn't calculate yet.
Okay, but in general, do you expect them to be the same?
Yeah, for reductive groups, definitely. Yeah, I also didn't, I need for honesty to mention, I also found the work after that of Midorikawa, which someone told me it says it means Green River, which seems to say something similar. Anyway, you can look at his paper, but I think he has a mistake on the first page. Anyway, I don't want to comment. You can. I just say that I found something looks similar, and you can look at it if you want. Yes. So your question is, of course, we expect for reductive groups. For other groups, we don't have too much intuition.
I see. And my second question is, what is the application of this? So.
I don't know.
Okay, maybe otherwise, what motivation, where does this come from? So you explained that it is a very natural generalization, but do have some.
I think, I don't know what, if I try historically, motivation, well, it's not really motivation, but somehow we got to it in a convoluted way. I wanted to understand Bernstein morphism better, and as a morphism from L2 to L2, and then you have first basic question, what enters L2, and somehow we got to this more basic question and degraded to this basic question. But yeah, I'm not sure.
But it's a very basic question, I think. It doesn't.
Yeah, it's very basic because yes, what is a characterization of tempered representation? It's kind of a question which people like to say, kind of it doesn't have a general answer, it seems, for a general group. It's kind of slightly vague. In terms of growth, for example, you have the definition of tempered, and it means, the standard definition in the Feld topology means that on compacts, you are approximable by matrix coefficients of the regular representation. But this sounds kind of very not clear condition in several respects, but also in the respect that it doesn't talk about growth on the group. It's somehow on compacts, you are approximable. So it's very not clear how to work with this condition. So I guess I had this slogan that tempered is on the verge of being square integrable, and it's kind of not clear in general what this slogan, how to interpret this. So for example, you also have the criterion that your matrix coefficients need to be in L2 plus epsilon. But for example, such a criterion seems to me is kind of pointless. For example, for a minimal group, clearly it doesn't make sense because you know, the trivial function one is not in L2 plus epsilon. Anyway, it seems like simply a coincidence for reductive groups because matrix coefficients are very nice functions, regular. So maybe this is not good. And of course, this high function, so it's also very specific to a rich structure you have for the group. So I guess it's some natural question in general how to understand temperedness in terms of growth, which has no general answer maybe. So maybe this definition of C-tempered is an attempt at some general structure which you might have for.
Great, thank you very much.
Thank you.
Thank you.
And any further questions? Okay, so thank you, Sasha. And so in 2 weeks, we don't have a seminar, but we should have one in 3 or 4 weeks. I'll send an announcement.